Welcome to the CCARC 2019 series of lectures. Dr. Vickal Kumar, who we know from the past, talking to us about the impact of space weather.
Yeah, thank you. Can everybody hear me? Yeah. So, we are really honored to be here. We have been visiting this field day for the last couple of years, and we often learn a lot from you guys. So yeah, thank you for having us. I'm also feeling a little bit uncomfortable today, just because I'm speaking to some of the experts in this area in terms of HF. So I'm hoping to learn something or a lot from you guys as I present. So feel free to challenge what I got here, and feel free to give me your feedback. We want to improve our service. At the same time, we are really excited as a Bureau of Meteorology, because just recently we have been selected as a global center to provide space weather services for the aviation industry through ICAO. So lots of good things are happening at Bureau. So in terms of this talk, I will have the talk structured in three layers. So in the first part, I'll talk about the space weather events, those that can affect the aviation industry. And in the middle part, I'll talk about how will we deliver this service to aviation industry using their own network. And by this I mean ICAO. So I don't know how much you have heard about ICAO. So during this presentation, I'll try to give a little bit of a background what ICAO is and how come we got selected as a global center. And finally, I'll go into the little bit of the boring stuff, which is talking about the science behind this service. So whenever you get little bit off track, or you feel like, oh, I'm not understanding this, just raise your hand. And I want to make this talk very interactive, and yeah, so the idea is I want you to enjoy this 1 hour or 40 minutes, it depends on how long the presentation goes. Yes, so with me. So in terms of space weather events, what are these? I believe many of you know what I mean by space weather events. These are storms that occur out in the space, and these are of different magnitudes, and they can affect technologies in different ways. So in this plot here, I have got the probability of a particular event occurring on the y-axis, and down on the x-axis, I have got three different types of storms. Now I borrowed this figure from a magazine, and what it's showing is the usual bad weather type of event. They occur in general between approximately 10 events per cycle to somewhere around 100 or more. Now, by a cycle, I mean a solar cycle, within 8 years is around 11 years. So when these sort of events occur, which are associated with weak C-class, M-class flares, small CMEs, and other things associated with the coronal hole and things going on the sun, which produce a weak storm, such type of events do not affect technology to extent where it cannot be used. So the next category is the severe and extreme space weather events. Now in terms of frequency, these events are typically around one event per solar cycle, but if the sun is very active, we can have as much as one event per year. Now looking at the most recent one, the September 2017 events. Now if you have been using HF during that time, I think around the 6th and the 7th of September, you might have seen that HF was not usable for an hour or so because we had a strong X-class flare. So such type of events, they fall under the severe to extreme category. We also had the Halloween storms, the Quebec storm. The Quebec storm, it took out the hydro power system in Canada for around 11 hours. So such type of events are categorized as severe. And finally, we have the Carrington type event, and again, you might have heard of this. So Carrington type event, the last one occurred in 1859. So these sort of events in terms of frequency are 1 in 100 or a 500-year event. If this event occurred today, it will send us back to the 1960s. It will basically wipe out a number of satellites, so we'll not have GPS navigation for months. We cannot fly. So that's where what you guys are doing in terms of HF will become really, really important. It will become the means of communication. So please, whatever you've been doing with HF, continue doing that, because one day we'll go back to the technology. So looking at the Carrington time event, even though it's 1 in a 500-year event, there was a recent event that was much stronger than Carrington, and it occurred in 2012. But the good news was it occurred on the far side of the sun. So the explosion happened, but it didn't affect us. So imagine this explosion was delayed by 8 or 10 days, would have surely sent us back to the 1960s. You guys would have been so much in demand then. Everybody would have gone back to HF. This is the way we're going to send signals. So please continue working in this area. I think this is the vital backup system, and it's very, very easy to put together compared to something that's based on satellites. Now, so in this talk, I'll be focusing mainly on the severe to extreme and super extreme events, and these are the events we want to generate warnings for the aviation sector, and that's when the systems will not be used. So looking at these severe to super extreme events, where do they come out from? So where they come out from as space weather forecasters, we tend to look at these dark spot regions on the sun, and this is what we call as the sunspot. Now, it depends on its magnetic complexity. These regions can generate a X-class or a stronger flare. So this sunspot region is for July 22nd, whereas that flare is from a different event, so the dates are different. Now, when we have an active sunspot region, it triggers a flare, and post flares we can have a strong CME. For example, this event generated a CME on 23rd July. So the way we look at CME is using this chronograph imagery. So this is a 2D picture of the sun. So looking at the sun from the earth. So yeah, it's like, so when we have a halo CME, imagine a massive volcano occurs in the center of the sun. Now, because it's a 2D picture, you will see eruptions, this sort of flux coming out from all the regions. So when it's halo, there is a good chance it will hit Earth. But sometimes, if the CME is located here, the eruption is located here, so when the flux comes out, when you look at it in a 2D sense, it will as if it's coming out from this region, and that's what we say as a partial halo CME, and that also has a chance of hitting Earth. So as forecasters, we tend to model this event and predict when does it arrive and what will be its magnitude, etc. And the flares, unlike these guys, where we have a heads up of 3 days or as small as a day, the X-class flares will arrive at Earth within 8 minutes or so. So basically, when the flare occurs, you will see systems will go down. So basically dividing this into a flow chart. So sunspot regions can generate CMEs and flares. Now, the impact of CME on Earth not only depends on how much mass is in this eruption, but also depends on what is the magnetic configuration of the sun compared to the magnetic configuration of Earth. Now, just to break it down in simple terms, so for Earth, we have magnetic fields going from the south, the north, so we have this dipole arrangement, whereas sun is very, very hot. So its magnetic field lines can spread all the way to Earth and beyond it. So you can imagine this as a current sheet. So this current sheet could be this way, or this current sheet could be this way. So if the current sheet in such a way, if the magnetic field coming out from the sun, so I guess you guys will understand this much better than me because you are engineers. So correct me if I'm wrong. So you have the current sheet, so there is magnetic field associated with this. And so it comes out from the sun and then goes back to, so that we cannot have something called like a monopole. So as these fields interact with the Earth's magnetic field, so cases where the two fields are what we say antiparallel, which is the arrangement here, it will cause the Earth's magnetic field lines to break and reconnect with the sun's magnetic field lines. So when there is the arrangement, most of the energy that's coming out from the sun can enter straight into our polar regions and into the Earth's ionosphere. On the other time, when there is a CME, but the sheet is below the Earth, so Earth is above this, in that case, the connection doesn't occur to that extent. So that's why when we monitor the effects, we not just monitor this, but we also look at what is the sun's magnetic field at the time the CME arrives at Earth. So it is this part we have lots of difficulty in predicting. And that's where sometimes when we say it's a severe storm is expected, but by the time the storm arrives, the current sheet is below Earth, we don't see storms going up to that level. On the other hand, there could be a weak CME, but if the BZ condition, if the magnetic fields of the sun is towards the sun or anti-parallel to the magnetic field of Earth, that's when we can have a massive storm, even though the original CME was not that strong. So those sort of two factors that are really important in predicting the strength of the geomagnetic storm. So whenever you see our warnings that there is a geomagnetic storm in progress or something is happening and it didn't happen really, just because we got our BZ prediction wrong. And we always try to predict the worst possible. So most of the time when we see an ROL alert and nothing happens, so please do understand this is the difficulty we are having. Now apart from geomagnetic storm, there is also radiation storm. Now these are due to particles, high energy particles going out in the space, and they can affect satellites. It can cause the solar panels to break down. It can cause deep dielectric discharge, so the chips within the satellites can get affected, etc. Did you had a question? Yes. So and so this is what we say as radiation storm. So radiation will have a huge impact not just to spacecrafts out in space, but also in the polar region. So these days, the aviation industry is trying to fly, suppose flying from Perth to South America. The easiest path is to go over the poles. And when you go over the poles, during a time when there is a storm, there is a huge amount of radiation. So those sort of warnings and services we are trying to develop for aviation, trying to advise them to fly today or not to fly today over the polar regions, etc. So that's what you will see next coming up. So looking at flares, so unlike these guys, few days, this can arrive in few minutes. So these are ones associated with X-class flare, shortwave fadeouts, and post flares, we can still have radiation events. So the next question is, so we understand all of this, we understand the science behind it. How can we get administrators, policy designers, governments, and aviation industry on board to take heed of this warning? Now, even though space weather events are very rare, this surely can have a huge impact on our economy and on ourselves if we are not prepared for that. So that's why we have started talking to several agencies, and one of them has been the aviation industry, and this is through ICAO. ICAO is the International Civil Aviation Organization, a UN body consisting of close to 200 odd countries. So looking at just a little bit of a background what ICAO does, and then I'll explain to you how we became a global center. So what ICAO is, it is concerned with everything aviation. It sets the rules, it's concerned about the safety, it's concerned about the capacity and efficiency of aircrafts and security, economical and other environmental factors. So as part of Bureau of Meteorology, we have been working very closely with the local aviation sector. So we are the reason sometimes why your flights gets cancelled, or you are not able to reach to the right destination, just because we are very concerned about safety. So some of the things that we do supply the local aviation sector is thunderstorm and lightning warnings. So flights do get cancelled out because of that. Volcanic ash advisory is also coming out from Bureau, and fog advisory related to aircraft. So what is the new service that will be adding to this is space weather. So hopefully we are not the cause of your cancellation of flights within the next 10 or 15 years. But if there is a cancellation, it is just because of safety, and we're trying our level best to make sure that when we issue a warning or alert, it is really real. So this ICAO became aware of the need of space weather advisory back in 2010, and that's when all the discussion has started. Now I will not go into the details of what these different processes were, but just a quick summary. They started developing what are the standard procedures and what should be the way we should do the warning, so that the aircraft pilots can understand what it means for today. Now we do observations, we do numbers. As a service provider, it is really important for us to convert those numbers to decisions that the end user can apply. So if you say that today there is a CME with a KP index of 8, the end user will ask us, so what does this mean to us? So what? So what we want to do is to convert those numbers into things like don't fly over this region, or if you are flying, you'll have HF problems, etc. So that's the goal here. We want to convert our observations into things that will make sense to the end user. So that's what was done in all these SARPs and annex. So in 2016, we prepared ourselves and got ourselves audited for ICAO to become a global center. Now you might be asking why Bureau of Meteorology should become a global center. Why not anyone else? So for us, so the new Bureau strategy is we want to be engaged with our customers. So customer engagement and value and impact are the two key things we are trying to focus on. We are not trying to chase wealth, or we are not trying to focus on private sectors. What we want to do is develop a service that is useful for mankind. So that was the main reason why Bureau got itself involved in this sort of service. And of course, the risk for us not doing this is as you know, space weather is a very global phenomena. Now, down the track, if we don't get ourselves involved with all of this, there is a possibility that you as taxpayers might ask, we really don't need a space weather services in Australia. Why don't we go to US? Because it's a global phenomena and we can get all the information from one place. So it was more like a survival as well as a impact and customer engagement. That was the reason why we got into this. So in 2017 we got audited, and 2018 Bureau in a consortium with other space weather centers became a global space weather center. So what ICAO has is right now 3 global space weather centers. There is the European one, PAXUS. This is a consortium of all the European centers that do space weather. There is the NOAA SWIPSI one, so the US one, and then it's us. So it's a consortium between Australia, Canada, France, and Japan. So these are our 4 partner countries. So the way these global centers will operate is every 2 weeks, a particular center will become the main provider of the space weather advisories, and the next after 2 weeks it gets shifted to the next center, and so on. So while suppose if NOAA SWIPSI is the primary provider for the 2 weeks, we become the backup or the secondary backup. So if somehow the other their systems fail, we have to step in and start providing the service. So that's the sort of thing, that's the coordination required. We will go live around the mid of this year. And I'm one of the crazy scientists behind all of this work, developing all the models, but I'm not the lead person who is doing all the coordination. And we'll also have 2 regional centers. So at this stage, China and Russia will become the 2 regional centers, but as systems grow, as demands grow, they might also become global centers down the track. So looking at the Australian, Canadian, France and Japan arrangement, we'll be providing services in these 3 regions. So there is the radiation, HF comms and GNSS. So when it comes to radiation, Spectra is the French guys. They are the one who will be leading this effort, just because we don't have any capability in terms of developing a model in this area. But this is one area we want to walk in, and we need some data and modeling support. So radiation is one of our weakest areas, so we are a backup to this service. When it comes to HF, this is our strength. We have been doing this for close to 100 years, and we will be the one who will be providing all the service to globally in terms of HF comms. And GNSS will be providing regional advisory based on our network, but we won't be the global center. And the French, again, will be leading that, and we are a backup. So before I go on and explain a little bit further, there was supposed to be a video that explains why it's important. Let's see if it plays.
Space weather affects technologies.
Clear on your final.
As conditions develop, we put out alerts, warnings, and watches to our customers so they can take action.
There's different types of impacts on communication systems. And the HF, we call the high frequency, which is that band of communications 3 to 30 megahertz. But it's a very important band of radio communication because it's used widespread. It's used, for example, by the airlines.
HF radio is most commonly used for position reporting when you're going across the ocean airspace, which is devoid of radar. And ATC can't see you, so it's up to you to report your position and your altitude and your speed.
HF works great most of the time, except during a big flare. And during a big flare, that HF communication capability could be gone within a minute or 2. So as soon as we see something happening in there, or we see a flare, it's one of the first things we do is alert the aviation community, hey, big flare, HF's going to be impacted.
Once we know that there's an event going on, then the aviation industry and the airlines can react to that. They can alter their routes over the poles. They can lower the altitudes that they're flying at, or maybe decide not to fly at all in the interest of their passenger safety.
So that's just one example of how the HF is used, but the emergency response community will use it a lot too. It's one of their primary backups.
When you've lost connectivity between certain government agencies, it gives you that long-range coverage to talk from out of state to federal governments or from the FEMA locations to the state emergency operations centers.
So if we've got a big hurricane impact in the coastline, whatever big city, we've got the cell towers down and whatnot, we've got emergency communication folks in there. Those folks are very familiar with space weather and how it impacts their systems.
Here in recent years, it was used during Katrina when we had a lot of communications outages down there. It was also used during Hurricane Ike. There was an outage of the telephone circuits with the Texas State Emergency Office, so it was used in both of those situations.
So when we talk about backup, especially for the airlines, typically they'll have SATCOM, so that'll be satellite communication.
The satellite technology that emergency responders use could be GPSs, could be satellite phones, satellite data terminals.
space weather events can impact SATCOMs. The impact can range from a nuisance to loss of a spacecraft. So we will give them the heads up. If we have space weather events, flares, whatnot, they need to know what's impacting their systems. Situational awareness is key. Time is of essence to these folks. Again, it's life and death.
Alright, so this video was from the NOAA SWIPC guys. So the way NOAA SWIPC operates is pretty much very similar to the way we operate. And just because they got a nice video up here, we thought we'll just borrow it and use it in this presentation. So you can see the amount of impact space weather can have on different technologies, not just HF, but also satellites. The positioning is also crucial. So the error that we have in the positioning system, the main source of the error is space weather. Those variations in electron density are from the satellite to ground base, and so the systems that are in place, they know what is the configuration of the input and also at ground station. So where the error is how much variation is in the ionosphere, and that's it's difficult to model, and that's what is affected when we have a major space weather event. So jumping back to the presentation. Apologies. All right, so next I'll talk about the different services. So under the HF system, we need to provide 4 advisories. The first one is what we say as the HF depression, and the next 3 is related to absorption. So bear with me, this is a little bit sciencey. So if you do get lost, please raise your hand, and I will try to break it down even further. So what this plot is showing here is the bandwidth the ionosphere can support at any given time. So during the daytime, when there is a lot of solar ionization, there is a range of frequencies that can be returned from the ionosphere. And during nighttime, when the solar flux ionization disappears, we have lots of recombinations. So the lower D and E region of the ionosphere will disappear. It is only the F region that survives, and it survives because at F region we have a large separation distance between the positives and the negatives. So even though they start recombining, all of them don't manage to recombine in time. So we do have some bandwidth left at night, and which is what you see by this picture here. Now, what happens during a geomagnetic storm, as this plot is showing? So the dotted line here indicates the onset of a storm. Now, these storms can have a KP of 5 or more. So depending on the local time of storm onset and other factors, seasons, etc., what happens during a storm in general, for the first few hours, the ionospheric density is in fact enhanced. And as there is over time, as there is a lot of energy precipitating in the auroral region, this causes the winds in the auroral region to start spinning out and moving towards the mid and low latitude. Now these winds carry lots of what we say as depleted ion and electron density. So as these winds come down with depleted ionospheric electron density, they cause enhanced recombination. So there is lots of losses of charges. So as a result, if you are using a particular frequency that you normally use during that time of the day, that frequency is lost out in space. It never returns because all of a sudden the required bandwidth has been suppressed. So these depressions can last for a day or 2. So post storms, if you see you cannot use HF, that is the reason why it cannot be used, because the ionospheric densities in the ionosphere has gone below the expected level and signals get lost. In terms of statistics, we have recently completed a study using 50 years of data for around 500 to 1,000 different types of storms. So I will not go into the detail of what this plot is showing, but in a very simple terms, this is from the South Pole to the North Pole, and this dotted line here is the onset of several storms. So the part as HF user you should be worried about is this blue region. So you can see, so storm starts, and after some 6 hours or so, we see the depressions from the high latitude regions, they propagate down to the equator. So that region here. So if you are hoping to establish a link in the high and mid latitude regions using HF for storms, there is a good chance that you will not get that link. So that's when, in terms of our systems, we start issuing warnings, and we'll try to advise the aviation industry that if you are using HF in the high and mid latitude regions, there is a good chance the link will not be established. So in terms of a simple concept map, the way we are driving our prediction, so we look at the geomagnetic index. Now, just because sometimes the depressions can occur without a storm, because our data is driven by ionospheric observations, sometimes because of occurrence of things like spreadicky and other phenomena, the signals will not propagate all the way. So all of a sudden we will see much lower frequencies. Now these depressions are not because of a geomagnetic source, but for something else. So we wanted to suppress those sort of warnings. So our initial trigger is we needed a storm. The storm has to have occurred some 3 to 4 days prior to our system generating a warning. So that's the first input that goes in there. The second input is our global T-index and ionospheric maps. So you might be familiar with that. So we look for features like a particular region should show a depression of 30% and lower compared to the monthly predicted levels. Now, as you see, based on these criteria, we are really tightening our depression warnings. So we really don't want to issue warnings every second hour or every second day. We want to issue the warnings when it's really, really significant. So when we have a KP stronger than 5, and we start seeing large regions of depressions below 30%. So by large region, I mean in terms of longitude 15 degrees and in terms of latitude 30 degrees. So those massive areas, when they start getting affected, that's when the advisory will go through. And the lifetime of these regions should be 20 minutes or more. So if it's spotty and disappears the next time, we will not be issuing warning. When it's lasted for close to 20 minutes, that's when we'll issue an alert. Apart from this, apart from the maps, we will also use ionospheric data, those direct observations from different sites, as another check that these depressions are real. So by ionospheric data, I mean those individual zones that are on our website, and we also have a network with our global centers. So in a similar way, like the way we process the maps, we are processing the individual ionograms in the same way. So suppose the maximum frequency now is much lower. It's 30% lower than what is expected at this time of the day, and the zone is located somewhere around or in the vicinity of the region where we have found a depression in the map. That's another check that now we are ready to issue the warning. And so once these three pieces of the puzzle are all positive, that's when we issue a space weather advisory. So in terms of advisory, this is a template, a sample of how this advisory will be issued. Of course, because we're doing this for aviation, and if it's really successful, to do a similar thing for the general public. So in terms of our HF user, you might be using the T-index maps, etc. But down the track, you might also have access to this sort of information. So what this advisory is a bunch of numbers for us to track what advisory is generated. What is really important is this region. So it's very simple at this stage, because what the pilots want to see is just a polygon. this is the area I'm flying, I'm in this area, I might have some HF problems. And we also do a +6, +12, +18 and +24-hour forecast. What do we think is happening? So moving on to the next 3 advisories. So these are ones related with absorption. So unlike depressions, which affect the upper level of the HF bandwidth, when we have absorption, it affects the lower frequencies. So what an absorption is, imagine, do I have to explain to this group what a flare and how it can cause absorption? Please pardon me if you think it's just way too simple, but I will try to cater for the bigger group. So do give me a heads up if you think, all right, let's just move on. So what happens when there is a flare is, so it's a huge amount of energy pumping into the Earth's ionosphere in a short amount of time. Now the different regions starting from around 80 kilometers all the way up to 400 and higher have got different density gradients. Now in the lower region between 80 to say 100 kilometers, there is lots of particles. So when there is ionization going on there, they quickly separate and quickly join. So all of a sudden the net effect is the electron density levels are low. So it's not able to reflect a wave. So as you go up in the F region, when there is ionization, there is charge splitting, and they go far apart, and all of a sudden we have a net electron density, and that's when the higher frequencies can be reflected. So what happens during a flare is it pumps in a huge amount of energy in all these different layers. So when you go down to the D region, where there is lots of particles, all of a sudden we'll have lots of positive and negatives. So the recombination takes a while to happen. So all of a sudden we have a huge amount of density in the D region, and as waves go through, they get absorbed. So they get bited out, and that's what we call as a short wave fade out, because within an hour or so, the charges come together again, and it becomes more like a neutral region. So that's why after an hour or so, the waves can start going back on again. So that's the concept behind flares and why it affects the lower region, because the lower region is the one that's packed with particles. So I hope that kind of makes sense. So we have in-house models. So when there is a flare, we run our model. So this is the September 2017 event. We had an X-class flare, and this is so flare effect is on the day side. So I hope you could see the map. Maybe the color is not really good. In fact, there is a better version of this one, and this is thanks to some of you guys who are part of the Whisper network. So you can clearly see that the flare effect is quite prominent in the Whisper network. So this is before this flare actually occurred. So according to the time of the flare, we expect lots of problems in this European region. So this is just before the flare, and as soon as the flare hit, you see all those networks down there has gone out. And then after some 10 or 15 minutes, now it's coming back on again. So yeah, so data that you guys are part of or collecting is sounding to be really useful in terms of validating our model, and that's one of the areas we want to work with you guys further. So there is a plan of putting a transmitter at our Sydney office, which will be part of this network, and hope you guys can listen to it a lot more. So I can see there is some connections coming out from the Shillong region, but once we put our own transmitter, we might even be able to have better predictions with the help of you guys. So yeah, keep up with the great work. So in terms of, again, concept map, how we'll be generating these flare warnings. So we'll have we'll monitor the Gauss X-ray flux. So so these are the different types of flares. We have A, B, C, M, and X. So what is of prime importance is these X-class flares, and when this happens, that's when we have a possibility of a widespread fade out. So when there is a X-class flare and larger, that's when it will trigger the warnings in our system, and we run our models, and this is just a test case, and it shows that in this region, so what the color is showing is, if you want to establish a connection now over the Australian region, this ILF means that your frequency on a 1,500 kilometer path has to be larger than whatever this color is showing. So these yellows mean, say, around 14 megahertz. So if you want to have a connection in the time of flare, so your frequency has to be larger than 14 megahertz to have a link. So this is the sort of information we're planning to supply. And again, we'll be issuing the advisory. Down the track, we are hoping to ingest the WISPA data into further validating the model. So if the WISPA data is indicating there is a strong fade out here, we'll try to implement in our model, because these models were developed in the 1970s, and since then no one has been as smart as those guys to fix it. So yeah, we just need to work a little bit harder to come up with more advanced techniques to better predict these models, these fade outs. So the next effect is again an absorption related, is what we say as a polar cap absorption, PCAs. So this is a phenomena that affects the high latitude region, and this sort of events are associated with what we say as a proton event. So these events usually occur post a strong flare or post a strong CME. So this is, flares can last for about 8 to 10 minutes, but post flare we can have lots of slow moving protons coming towards the Earth. So in this example, the flare has triggered and has come down, and now you see this X-ray proton flux going, and they are leaving for not just few minutes but for about 2 days. Now when that happens, we'll have lots of particles connecting into the Earth's polar region, gyrating along the field lines and entering into this region. So the effect is very similar to a flare. They get down to the D region where they increase the ionization, and when there is a huge amount of ionization in the D region for prolonged periods, I'm not talking about an hour, but this will be for a couple of days, you won't be able to have a link in the polar regions. Now in the polar regions, for the aviation sector, HF is the primary means they communicate, because there is no SATCOMs up there. So for us to get these warnings out there is really, really important. So this is an example of what happens to the signal when we have a PCA, a proton event. So that's where the event started, and for 3 to 4 days, the links in the polar regions are very, very weak. In terms of warnings, we'll look at the proton flux data. So this is our model prediction. Now I did this run for our summer, so during December, and so when we have a PCA event, you see the South Pole, because we are in our local summer, we see lots of reds. So if you are sending a signal here, it's better to use the highest possible frequency licensed to you to establish a link, because the lower frequencies will certainly get absorbed when there is a PCA event. So during winter, these effects are slightly weak. And again, we'll issue a warning when those two criteria are met. So the other data we are hoping to ingest into this model is the ryometer data. So ryometer is observing cosmic flux in the high latitude region. We have a network of 4 operating in the Antarctica region, Casey, Mawson, Davis, and at Macquarie Island. So we're hoping to ingest that data to further improve the model prediction. Finally, to the last set of advisories when it comes to HF, this is related to the aurora. So when we have a large geomagnetic storm, it will again pump in lots of energetic particles. So you will see this aurora in the northern and the southern hemisphere region, and that's just a picture of that. So here we look for KP index greater than 9. Oops. And what it produces is these two auroral ovals. So let's say if you're sending a signal from South America to Perth, and there is an aurora in place. So as the signals go through this region, it will suffer some absorption. So there will be a weak link, or in sometimes the signal is completely lost. So those are the warnings that we get. So moving from HF to a GPS-based warning system. So what this picture shows with dots there is our GPS receiver network. So with these we monitor things like ionospheric scintillation. So when it comes to GPS-based disturbances, there are 3 types of disturbance that one has to worry about. One is the low latitude equatorial plasma bubbles and gradients. So the equatorial plasma bubbles has been a area for research. This is a new and growing area. There is some possibility that these plasma bubbles are actually generated by atmospheric phenomena such as gravity waves associated with thunderstorms, etc. So there is a good chance there is a connection between large atmospheric phenomena, say a tropical cyclone or a depressions, because they can generate gravity waves that can propagate all the way to the ionosphere, and when that happens, there is a chance it can generate what we say is these bubbles in the ionosphere, and when these bubbles occur, it causes rapid fluctuations in the GPS signal, and that is what we say is scintillation. So definitely there is this link that we have to study, but for our concern, we are not interested in the source. It would be good to know the source, but what we want to do is when there is these bubbles in present, when we have this rapid fluctuations, we want to issue warnings to the aircraft industry. And as you know, these days aircraft, they will basically try to use the same path as they fly, because that is the most efficient way to fly. And while doing that, the separation distance between corresponding aircrafts could be as small as around 500 to 2,000 feet. So if they get their positioning wrong, there is a chance that things can come together. So what we want to do is we want to issue some sort of warning and alert that today, please be extra careful or may use a larger separation distance when you are overflying. So those sort of errors associated with S-buzz that GPS scintillations can generate. In the mid-latitude regions, we have traveling ionospheric disturbance, or what we say MSTIDs. Again, these are associated with weather fronts that can propagate all the way to the ionosphere. And in the high latitude regions, we have auroral effects. So I'll not go too much into the details in the interest of time, but this one here shows scintillation occurrences in the low latitude region. So these reds are over Darwin and up there. So if aircraft is flying, they will have some navigational problems because of this scintillation effect. Moving on to the last effect, this is the radiation effect. Now this is an imaging area at Space Weather Services. We don't have our model with us at this stage, so we are combining with the French team. They have more advanced understanding here. So in general, based on a NASA study, if you have collected 100,000 frequent flyer points, you have basically taken 20 chest X-rays. So that is the amount of radiation that's out there. So the higher one flies, the more radiation is up there. And more importantly, if there is a coronal mass ejection, and if you are flying post that, especially in the polar regions, there is the good chance there will be a large amount of radiation. But don't worry, the aircraft industry is well aware of this, and whenever there is this sort of warning, they will deviate their flights and they will not go in the polar regions. But overall is the awareness that's really important. So with that, I will finish my presentation. So just to summarize, we are issuing this bunch of services to to aviation. And right now it's going directly to ICAO, but down the track we'll be publishing this sort of information on our website and the general public can use it. So so if there's any question or there's any confusion, do let me know. And please, or if there is any feedback in regards to our maps, I'm happy to hear it, and we always go back and do some changes. And because of you guys, we have done a lot of changes on our website. I don't know whether you have noticed it or not. There is things like you can see an evolution of the ionosphere for the last 7 days and not just the current condition. Thank you.
Thank you very much, Dr. Kumar. Another wonderful presentation. And I've got 2 of the certificates to present to you because you gave another lecture here 2 years ago.
Yep. Thank you.
Well done. Thank you.
Another question. One question. With the magnetic Earth moving across towards Russia, is this affecting any of your readings, especially for navigation?
That's a great question. I'm not sure at this stage. So the magnetic field movement and modeling, it is a growing area, and that's something that we should be concerned about. Just to a little bit sidetrack, we are now part of this national infrastructure project, and Geoscience Australia is in fact leading it. And because down the track we'll be having things like driverless cars, and everything will be pretty much driven with GPSs. So the point you have raised is a very valid one. We need to understand how the magnetic field configuration is changing. So at this stage there is not much work that we are doing, but what we are doing is we are helping Geoscience Australia develop a model that can be used to then predict GPS accuracies to a centimeter range. Not just few meters, but we are coming down to centimeters. So when farmers use their tractor and they design the track they are trying to use, it will be really, really accurate. So that's sort of, but again, the movement of the whole tectonic plates becomes really, really important.
It would be more concentrated in the North Pole and the South Pole.
Yeah, I hope I could have answered, but yeah, I don't want to hypothesize, but yeah. Yes. Thank you for that question.
Just with the scintillation effects with the GPS, in simple terms, what is the effect of the scintillation on the positioning?
Yep. So yeah, again another great question. Imagine there is no scintillation. So the way GPS works is you need at least 3. It's like a triangulation, and that's how the coordinates is determined. So imagine this particular area, there is lots of bubbles and lots of irregularities, and it causes scintillation. So because of that, the signal is delayed by the time it arrives. So the way the positioning is calculated is simple distance time thing. So if one path has a longer time than expected, even though in reality it should be shorter, so that is the sort of error that gets into the positioning. So what our role is to help these satellite systems to come up with a better model that they can feed into their observations, so that it can correct for those delays, it can correct for those scintillations. So at this stage, this hasn't been fully implemented, but as I was explaining to the guy at the back, we are part of this NPI project, National Infrastructure Project, and part of that project is to reduce those errors in GPS links and bring it down to a few centimeters and not just to tens of meters. So right now, sometimes when you're using GPS, it will show, okay, my car is in the field when it's on the road, and it's just because of all those problems that's going on in the ionosphere.
BOM send out severe thunderstorm warnings on Twitter. Are you going to be sending out prayer warnings on Twitter for us?
Oh, yes, hopefully. So, yeah, BOM is a massive organization, so media and those releases are done by a particular group of people who are well trained to handle media, and our role is just to give them a heads up there is something going on. If you want to make it a big issue, please go ahead. And we don't want our phone lines to go crazy. But yes, those are parts of the ways.
Yeah, the flowchart cabinet long-term longitude prediction. So it's far improved than the old radio work plans today are used in the 60s and 70s.
Yes.
We have a chart.
Yep.
that give you 200 miles out of Sydney.
Yep.
You'll be on 3 megs. 500 miles you'll be on 8 megs.
Yep.
1,000 miles you'll be on 7 megs. And then you'll be working, say, Tahiti on 3 megs again.
Yes.
There's a chart massive.
So are you talking about the HAP charts?
Yeah.
Yeah.
When you have the hacks and you're flying oceanic.
Yes. Yeah.
But HF's going out on as far as the main thing is all out from 8 years around the control evolution.
Yes.
Once the aircraft's on what's out of Sydney, it's moderate HF and contact prison on data link rather than the actual two-way comms on 8
Yep. Yeah. So I'll take that as a comment, or was there? Okay. Any further questions? Thank you.